We will begin. Welcome, everyone, to the New Jersey Astronomical Association. Over here still? Okay. And John, did you do the volunteer organization thing?
Yeah.
You did?
But you can do it again.
But do it again. It doesn't hurt for us to
Okay.
repeat.
All right. We have lots of people come to our talks and whatnot, and the crime that we find is that they're so excited at the end to go outside, they pass right by the donation box in the back, and we only need a little bit from each of you to keep us going because we're poor, and they don't pay me enough. So the thing is, if you can, please drop something in the box on your way out. That's all we'll be saying about this. So, welcome. TESS, one of NASA's latest missions, and what's that all about? Okay, it's a mouthful of words, but it's all about looking for planets around other stars. Now, when I was growing up, that wasn't even possibly thought of. We were happy that we found something called Pluto way out at the end of our solar system, and now Pluto's a dirty word, I realize that. But the thing is that trying to see planets around other stars, I remember every science teacher telling me, Paul, that's like looking for a fly speck on a 100-watt light bulb at the other end of the football field. So you're never going to see planets around other stars. But that's the wonderful thing about technology. Things get invented, things get developed, and it's just absolutely amazing what we can do now. I mean, you know, our phones, right? I mean, being a phone is like 10th thing down from what you really use it for, right? There's other things that it does. So it's the same thing with technology, with photography, or imaging as it's now called, and that's what I'll get into. But let's start with the basics first, which is our own solar system. Just a quick review. That's it. Okay? Starts with, of course, everything that's in the center is our sun. You can't even show the sun in its entirety because it's so huge. It would go around like that. But our solar system is kind of broken up into these quadrants, if you might say. The first 4 planets, which are right here, is the only terrestrial planets we have. Terrestrial meaning they're rocky, you can walk on them. So we've got Mercury, Venus, Earth, and Mars. And they're not all this squished together like this. The distances are not accurate, but the sizes are. Okay, so the sizes are relative. So yes, what planet is this?
Jupiter.
Right, Jupiter is definitely that much bigger than the Earth. And Saturn is right next to it, so it's no slouch. So that's why we call these 4 outer planets giants. Jupiter and Saturn are called gas giants because they're mainly made up of gases, methane, ammonia, hydrogen. It's only recently that we determined that these 2 giants are more icy than gaseous, so we call them ice giants. And I'll get to the outer ones in a second. But that's it. The 4 interterrestrial planets, the 4 giant planets, and then way out on the end, there's Pluto, which is a dwarf planet. It's still there, it didn't disappear. And there's comets, and this is really where it gets cold, way out here in the icy edges of our solar system because it's so far away from the sun. And the thing is that not only is Pluto out there in the comets, but there's something called a Kuiper belt. And what it is, it's when our solar system was being formed, kind of everything that didn't fit or got too close to a planet got flung out, and lots of the debris, so to speak, of icy particles and matter got flung out just past Neptune's orbit. And so there's actually a swarm of these things just outside of Neptune's orbit, of which Pluto is a part of. That's what happened with all the consternation about being a full-fledged planet. But it's there, and so are those icy objects way out there in this Kuiper belt. Who here knows what we get from the Kuiper belt? Go ahead.
Comets.
Comets, that's right. Because those icy bits that are out there, every now and then the planets don't exactly line up, but the tug of gravity from the planets will just pull on one of those icy bits just enough to, instead of keeping it in orbit, it'll just bring it in, and then what's the biggest gravity well in our solar system? The sun. And so it takes a direct route directly into the sun, and usually it misses the sun, but it passes us by, and then we see the beautiful display of a comet. I finally got to see one some years ago right from here when forgot the name of it now. What the heck was it? Anybody remember the comet?
Hayataki or?
No, it was later. Anyway. Huh? Hale-Bopp. Thank you so much. Right. Hale-Bopp. And it was beautiful. I was so happy to see it because they're rare. But that's where some of them come from. There's another area just outside our solar system where they come from too. I spoke too much about this stuff already. I hope I'm not boring you. Okay? But anyway, that's our solar system. But the thing is, what made it this way? Why this way? Why 4 tiny terrestrial planets in close to the sun where it's nice and somewhat warm? Why 4 huge planets way out in the icy realms, and then why all this stuff on the end? Is this normal? Nobody knew. Scientists didn't know up until just recently. And so that's why we're interested in finding extrasolar planets, planets around other stars, to see what do they look like. And this is just words basically of what I've been saying. They want to find out about this because just how the heck does gas and dust turn into planets? Because that's what happened. 5.5 billion years ago, there were no planets. Our sun was just created out of condensing matter, and then the swirl of gas, the solar nebula, so to speak, was spinning around that sun, and then over millions and billions of years, it cooled, and things collected together, and that's how we got planets, and meteors, and comets, and asteroids. But how exactly, nobody was here, so how does that actually happen? And the compositions and atmospheres of the different planets, they're very different. We now have an oxygen-nitrogen atmosphere. But Venus and Mars, what's their atmosphere made up of?
Nothing.
No?
Carbon dioxide.
Carbon dioxide, what we exhale, okay? The methane, you were right, is Jupiter, Saturn, and outward, okay? But why? So that's why if we look elsewhere, maybe we'll find the answers. The same thing about the diverse planet orbiting different types of stars. If we find certain kinds of planets around that kind of seem to match up with certain other kind of stars, that might tell us something too. We have a simple type of star. Our star is a G-type star, not all that big, and it gave us this distribution of planets. Well, what about other stars? So how do you do this? Well, I remember when the Jet Propulsion Library was talking about launching Kepler. Now, Kepler was a mathematician of old that developed Kepler's laws, but this mission was named for him. And what they were putting on Kepler was nothing but a big camera. Just think of how far your cameras have come, right, in just the past decade or two. I remember slides very well, right? Now everything is solid state, everything is CCD photography, right? So they applied that to telescopes. They had never telescopes in orbit. They had never done that before. So they took that same basic chip that's in your camera, and they just made them really, really big, and they added on them, and so I had a huge CCD chip, a detector for detecting images from a far distance. And they put it on a rocket, put it around this ship called Kepler, and they launched it out there. And its whole job was to sit there in orbit and just stare at one small spot in the sky for years after years. It did a survey for 4 full years, and as it kind of orbited the sun with the Earth, it just constantly stared at that one section of sky, a special group of stars. Why? Because it wanted to see if the light changed coming from those stars. Now on these slides, these are not my original slides, this came actually from NASA, you'll see the word flux, F-L-U-X. It's not the flux capacitor from going back to the future or whatnot. Flux is the name they use for the radiation and the light intensity coming from an object. So they use light and flux interchangeably here. So the idea was constantly look at the stars and look for changes. And this is what would happen. They would monitor it, watch it on the bottom, and then they would see the brightness or the flux dip. And the thing is that if you look at a star long enough, you will see the pattern repeat. Now, what 2 things can you see are being measured here by doing this? First of all, once it starts taking a dip, that's time. So something is going across this star, and it's going from that time to that time. So you've got time length now. You know how long it took to get across the diameter of the star or part of the star. Now you saw two objects go across this star, and we're simulating here, a small one and a large one. And so therefore, you've got a small trough and a large trough, because that's the amount of brightness that you're dimming. You're losing that much flux or that much light. What does that tell you? The size, exactly, right. The more you block, when I walk in front of a light bulb, it blocks out a lot of light, okay? When a little girl walks in front of the light bulb, it's just a little bit of light. That's all there is, size. But isn't that great? That ship was monitoring all these stars, and the thing is, that's all it did for 4 years, is constantly look for these changes in the intensity. And if it saw it repeat on a regular basis, you now had the orbit. You now had how long it went around that star. So you had the size, the speed that it's going around the star, and what its orbital period is. So you knew a lot about it already. And this was fantastic, because who knew that we could actually detect planets in this way? It first actually happened in 1999, right on Earth. Okay? There were scientists who were trying to do this with Earth-based telescopes. They actually tried this before '99, but this was the first published paper. And so this is what you do when you're working through the atmosphere. You get dots like this, and this is the intensity of this star. That's a star everybody knows, right? No, but anyway, it's HD 209458 is the name of the star. And the thing is that it actually measured, back in 1999, repeating dips in intensity on this star. So they published this paper. They saw how much it dipped and how long it took, and to their shock, they realized it was like a Jupiter-sized planet. But the speed at which it went across the star was only 3.5 days. 3.5 days to go across the star? That's awfully fast, right? It takes us 365 days just to go around our star, and we're not Jupiter-sized. So this is what became the term a hot Jupiter. Something very close to the star, but yet very big, and going around the star really, really fast. Sounds crazy. We never saw anything like that in that pattern I showed you before. Our Jupiter and Saturn are nice and comfortable, way out there going nice and slow and very cold. So this was wild. But what do we know? This is what was happening, and so that's what spurred on the idea of let's get something into space to look at this. Because when you're trying to look at something from Earth's surface, what do you have to go through? The yucky atmosphere that we have. Now, it may look nice and clear on a clear day, but as far as a telescope is concerned, it adds all kinds of interference, waving of the atmosphere. That's why stars twinkle. Okay, they really don't twinkle, but that's our atmosphere causing aberrations. So they really wanted to get something up in space. So there it is. That was Kepler. This is a picture of what Kepler looks like. And this is the area that it looked at. It was in a certain area near the Cygnus constellation. And I think it was, 150,000 stars that it looked at. And it looked at them for every 30 minutes for 4 years. That doesn't sound like a very exciting job, but the data that finally came in just astounded people. And again, I remember the press conference when this was talked about, when they were about to launch it. And the principal investigator quite simply said, we just don't know if there are any Earth-like planets out there. We just don't know. There could be a couple, there could be thousands. Just had no clue, but this was going to determine what it was. And determine it did. It was a statistical mission. It didn't do any particular science. It was just for counting planets. And Kepler's first measurements came in like this. Okay, I'm not going to bore you with lots of graphs, but now when they say Kepler 4b, 5b, 6b, they just had to name these planets something, so they gave them designations. But look, here's a short one. Okay, a tiny, tiny planet. This one's deeper, so it's a bigger planet. This was deeper still, but it's also short, which means it's moving fast. So look at all the data that you can get just from this CCD camera floating in space for 4 years. And this is what it found. after 4 years, as of just a couple of months ago, all those dots that you see in the middle, all the yellow dots are from Kepler. The other blue ones are from Earth-based observations. And not only did it find Earth-sized planets, but it also found what they call sub-Neptune planets. Planets almost as big as Neptune, but not quite. And the other ones were what they called super-Earths. The news loves to put those in the paper if you haven't heard that by now. Super-Earth discovered. You know, I keep thinking it's our planet with a red cape on and red boots and stuff like that. But they just mean it's a little bit bigger than our Earth. And we hadn't seen that before. But that seemed to be the predominant case. Of all the thousands of stars that it was watching, all of them, almost all of them, were showing signs of planets. But again, the majority was these type of super-Earths or, here they call it mini-Neptunes. Those are the two highest of all the planets that were found. And I think the statistic right now, and you can go online and see this, over 3,500 planets confirmed. All right, it's been repeated and confirmed. And there's still another 2,500, I believe, that are suspected of being planets. So the bottom line with this is, and shocking as it may have been at the time, planets are common around most stars. Most of them have at least one, if not more. You probably heard in the news about the TRAPPIST-7 system, something like that. Again, I love the news media. They love to grab headlines and just put them out there and let us guess what the rest of it's about. But recently they found a star. It's called, in the TRAPPIST system, that's a name. But it found 7 terrestrial Earth sort of type planets in it, 7 of them in one system. So the thing is that the amazing fact is there's lots of planets out there. In fact, we used to say things like what? For every grain of sand on the Earth, there's a star in the universe or in our galaxy. Now they're saying the same thing. For every star, there's a planet. So that's a lot of planets. Right? That's a lot of planets. Now, the next question is, are they in the habitable zone? What's a habitable zone? Well, the thing is, you've got to be just far enough away from your star to have basically liquid water for us to think of it as living life. We don't know of any other life that without water. Maybe it is. I watched a lot of Star Trek when I was a kid. So the thing is, who knows? Who knows? The little creepy hoarder or whatever it is that was silicon-based, why not? But right now, all we know is the biological life we know is that's something like on our planet, and it's all based on water and the DNA molecule. So the thing is that anybody know about Venus? Is Venus a nice place to be? No, because it's too hot, way hot, like 900 degrees. How about Mars? Is Mars nice and warm? Nope, it's cold, right? Like a minus 160 degrees sometimes. So you got that? Okay, Venus, too warm. Mars, too cold. What's right in the middle? Earth, just right. You see the simile I'm making here, and it's the good old Goldilocks tale. Too hot, too cold, just right. And sometimes they do call it the Goldilocks zone. Right? But if we want to be scientists, we'll say it's the habitable zone. Say that 3 times fast. Okay? So that's the next step. Let's analyze these planets and see where it takes us. And that's what brings us to TESS. Kepler's done its job. It's revealed to us that there are many, many planets out there. And it only looked in that tiny piece of sky. Just 150,000 stars. Not a lot of stars. All right? And so the thing is, that's why TESS was designed. And here's what it's going to do. This is TESS. Okay? And Kepler had one big, gigantic camera, one big chip in it that looked at that whole section of sky. But this one is going to have 4 cameras. And some of this stuff here is for the real camera and imaging people here, not me. But it's got a wide field of view. The apertures on the camera are only about 10 centimeters. They're small, but there's 4 of them. And it's going to, but the thing that's interesting though and fascinating about this ship is that these 4 cameras are going to be able to image the entire sky. Everything. The whole entire sky. So you say, okay, Paul, how's it going to do that? Right? Well, I will show you. Almost sounds like Jurassic Park, doesn't it? This is an individual camera. There's 4 of them, all right? I'm just putting it up here so you can see what the camera looks like. Here's the detector assembly here. Here's some lenses, and there's the hood to keep everything looking right. But again, it's only a 10.5 centimeter aperture. Seems pretty small. But 4 of them, and then what it's going to do is that for a given period of time, it's going to look at an entire band of the sky. What's that number there? Okay, what part of a circle is it? That's just about a quarter of it, right? And so it's going to look, say, from the equator all the way down to the southern polar region in one fell swoop. All those cameras will be looking at those different segments as it sits in orbit for about 2 orbits or like 40 days. And it'll image all that area of the sky. And then what it will do is when it goes into orbit, now I know it's a little confusing, here's the Earth here. When it first takes off, it's going to go out into orbit as far, just about as far as the moon. It will interact with the moon's gravity and then will swing out like this, and this will be the orbit that it will be in. Here's the orbit of the moon going around the Earth. TESS will go like this in between us and the moon, and it will orbit for 13.7 days, and it'll be what we call a resonance, which means it'll be equal with the gravity of the Earth and the moon so that it won't be flying off in different directions. It's a nice stable orbit, and so as it comes around, the Earth, this blue cone coming out is the cameras looking out. So for 2 orbits, 27 days, it will be here, and it will look out in this direction. And it'll look 96 degrees up and down, so I'll take the whole swath. And then after those 2 orbits, it'll be over here, and it's always pointing away from the sun, and now it'll look at the next section, up and down. And that's what it'll do. It'll go around the sun with us 13 times. It's basically broken up into 13 sectors. And by doing that, after a year, 1 year to orbit the sun, right? It'll cover the entire southern hemisphere. And then it'll repeat the option for the northern hemisphere. I don't know why they picked the south first. And it'll do the entire northern hemisphere. So in 2 years, it'll cover all the stars in the sky. There's one catch, though. There's always a catch. It's not looking at all the distant stars. It's just looking at the up-close bright ones. If you look at, this is us here. This is the search pattern, or no, this is the field of view for Kepler. It went out as deep as 3,000 light years. What's a light year? Roughly 6 trillion miles. Right? But it's far. So it went way, way out, and it caught all the stars in between here and 3,000 light years away. A lot of stars. But the thing is, we now know that those Earth-like planets that we're looking for need to be around bright stars that are close by, because then we can examine them better, and then we can see and learn more about them. I'll tell you that more in a second. So for TESS, it's just this area right here. Just for, what is it?
40,000.
No, it's something else. Sorry, I'm walking out of view here, sorry. 200 light years. I didn't commit that to memory. So it's just going to look as far as 200 light years. Now you may say, we're going backwards. No, it's only looking for the bright stars. So the bright stars are close, they're big, and that's what they want to look like. A lot of stars, though, for the entire sky. Okay, I love this slide, all right? If you're still with me, hang on to this one. So you find the planets. You know the basic, the period of their orbit and whatnot. And now you want to find out a little bit more about their mass and their density, because this tells you now whether it's a water planet, really a solid planet, or a gaseous planet, even though it's small or whatnot. And so there's something else that's amazing. If this is you looking up at a star, if a star has a planet or planets that's orbiting around it, believe it or not, the star wobbles. If you want to think about why that happens, think about a large person grabbing a smaller person by the hand and kind of like spinning them around or having them run around them. Do you think that person that's holding onto them stands absolutely still? No. They're leaning back and forth as the force of that little person is pulling on them. It's the same way with planets and stars. So as the planet is going around the star, it tugs on it. And that big star has to wobble a little bit. So the thing that's fascinating is we can see that. Now, can we see it visually? No, it's too far away and the wobble is way too small for us to detect visually. But through the magic of spectroscopy, we can look at the spectroscopic image of the light coming from the star. And when we study a star, we know it has certain bands that are in different light wavelengths. Without getting too complicated, there's a blue side and a red side as you scatter the spectrum across. And if you've heard this term, redshift, this is where it applies. If you'll notice, as this planet is going around, this is going up and down here with intensity, and this spectrum is shifting left and right. This is called the Doppler shift. The same thing with your hearing, with listening. When a train comes by and goes like that, what's the reason for the sound to change? It's the same horn. The fact is it's coming at you and then moving away from you. It's being compressed and then the sound waves are being stretched. It's the same thing with light. And so you're seeing that in the spectrum. These bands here should be like that. What's making them move to the right? What's making them move to the left? The star's wobbling. And now scientists are so smart, they can measure that wobble and they can tell exactly how much it's being wobbled. And from that, they can do all these other fancy charts. And that actually yields the radius and the density of the planet that's around the star. So all this just from examining the star from a far distance. You think that's enough? No. Now we want to know about the atmosphere of the planet and if it's got one. If it is, what's it made up of? So we do it again. We watch the transit this time. We're not looking at the wobble of the star. But just like Kepler and TESS will be looking for the light changing, now we'll look at it through a spectroscope and see how the different wavelengths of light change. You know, light's made up of many, many colors of the rainbow. You put the little prism on the light and you see it spread out. Well, there are detectors that can see just how intense those different spectrums are. So watch this animation now as this planet passes in front of this star. Here's the readings. But now, instead of just reading the light intensity, they're looking at the light spectrum. So it's saying that, did it disappear on me already? That's not fair. Let's see if I can get it to go again. Sorry about that. Woo, too far. So each of the different color spectrums has a different drop in intensity. And from that, they can look at the wavelengths and they can analyze that, and that gives them a hint as to what the composition of the atmosphere actually is. All this from just looking at that intensity. I'm going to pause now and see if there's any questions about what TESS is trying to do. Because that really is the end of what I want to talk about with TESS. Yes, miss?
So TESS just takes the pictures, is just an extension of Kepler, like it measures the flux.
Yep.
But you're talking about this spectroscopy will come after?
Yeah, and probably from ground-based, from ground-based telescopes, believe it or not. Because once they know where to look, then they can study it, and they don't have to worry about whether there's a planet there or not. They know it's there because TESS has proved it out. And actually, this is what's really going to help, which is why I have this up next. This is the JWST, or the James Webb Space Telescope. If you haven't heard about this, you will be very shortly, because this is a monster of an infrared telescope that's going to be launched from Cape Kennedy. It was supposed to be launched later this year. It's been delayed now into next year sometime. But you hear it touted as the successor to Hubble In a sense it is, but it's not the same kind of telescope. Hubble is visual. It has many components, but a lot of we see from Hubble is the visual pictures coming out, the beautiful pictures. But this one is mainly going to be looking at the infrared spectrum because we can see farther and see through dust clouds with this. But this will be the most powerful telescope in space. And just to give you an idea of how big it is, that's TESS giving a helping hand. And I talked all about that already. And, oh, no. Oh, I guess I didn't have it. I'm so sorry. I did a presentation at 2 o'clock today and I'm getting everything confused. This is as big as a tennis court. All right, so that's big. Right? The picture I thought I had here was everybody who worked on it standing out in front of a model of it, and it's absolutely huge. So think of a tennis court, and that's what this is. It's going to be an amazing engineering feat. It's going to be launched inside a nose cone of a rocket. It's going to go out just past the orbit of the moon, and then it's going to unfurl itself. And Jim, how many explosive bolts? How many pyrotechnics are on it?
It has more than the total accumulation of all prior explosive bolts used in all spacecraft.
So that's a lot.
That's a ton.
What we're talking about here is when, like, the Mars landers landed on Mars, they're held together with bolts. But there's a little thing of explosive in each of the bolt, and when it's triggered, the bolt literally breaks apart, and that releases a mechanism, and then things unfold. This thing has, you ought to go online sometime. I should have brought it here, I'm sorry. Go online and put it and take a look, and you'll see how this whole thing comes together. And it's like, oh boy, I hope everything goes right. But it's been tested, and it's ready to go soon, later this year or early next year. But this will be able to analyze the atmospheres of these planets that TESS is finding in the way I just showed you. So we're really going to see some amazing things come back from this when it's out there. Yes, again, Miss.
If it has so much surface area, how are they preparing against just like debris hitting it at such high speed?
They're beryllium mirrors and stuff like that, so they're pretty tough.
Yeah.
But right now, you got to understand one thing, and that's a very good question. But we grew up on Star Wars and everything, where every time Han is flying through some place, there's meteors coming around. We got to go through the asteroid belt and things like that. It's just not that crowded in space. There's definitely micrometeoroids that are coming out, pockmarking things and stuff like that. But it's built strong enough to handle that for a certain period of time. It's not going to last forever. You can say the same thing about the space station. Yeah, that's been up for so many years now, right now. And when the astronauts go outside, they see little, pock marks just like on our car windshield and stuff like that. But it's just built strong enough to take it. That's a very good question. Did you have a question?
Yes. The different period of times it spends in every zone, is that good enough for it to detect a planet? Because, normally a planet would take like 1 year or more than that.
It's a good question. The question he's asking is for when TESS is looking at a particular section of sky during those two orbits, is that enough time? Well, I said yes real quickly, but actually there's got to be a limit. So it's going to catch the planets that have orbits within that time, but if it's a slower planet that's on the backside, no, it's not going to catch it at all. But most of the ones that we're looking for are ones that are probably somewhat closer to the planet because they're probably in that habitable zone. And so they're going to see them, hopefully, in that time. There's just going to be so many stars that they're going to catch something. And that's the whole thing. They don't have to catch them all. Let's just get an idea. Let's bump up the survey that much more now to see what we've got. We now know we got thousands of planets. Okay, now let's find the good ones and start seeing what they look like. And then we'll learn more about how we got here and how our solar system formed. Do you have no idea?
Yeah. And if they detect a planet which is in the habitable zone,
right?
What if the planet is tidally locked to the star, and you tend to think it is Earth-like, but it may not have life because it's tidally locked.
What he's asking is, what in case they find a planet, but he used the term tidally locked. That's like our moon is to us. We only see one side of it. When you get something that's small, that's orbiting something very big, eventually it becomes tidally locked, where it orbits it, but one side always faces it at one time. And with the moon and the Earth, that's no problem. We just don't ever get to see the other side. But if you're a planet around a star, that means one side gets cooked and the other side gets cold. Yes. So what you got to do is you got to find a place to live on that little strip that's right between the hot and the cold. Seriously, though, the thing is, no, that's a consideration, and that could be the case. And if that's the case, yes, that gets it off the list. Although I've heard some scientists say that that wouldn't be the case because if it has an atmosphere, the atmosphere would be swirling enough around the planet to neutralize it. Who knows? But this is what's great. This is what these young ladies are going to study when they get out of college. And they're going to be looking at these planets and find out what's going on. See? But that's the exciting thing. That's why I like astronomy. It doesn't stay the same. It's so things change all the time. Who knew there were this many planets around stars? Who knew that we'd have CCD detectors this good that could detect slight changes in brightness of stars that far away? And then the thing I always say is, and what is yet to come?
There's a question back here, Paul.
Hmm?
The other lady has a question.
No, I was just sketching.
Oh. Sorry.
See, I knew that. Okay. So where's TESS now? Well, it's all packed up and ready to go. It's down in Cape Kennedy, and it's just next month, April. Come on, come on. I'm having a little trouble with this. Come on. There we go. April 16th. Okay. What is that? Oh, it's less than a month away. And my hero, Elon Musk, is going to hopefully launch it on the SpaceX Falcon 9. And away it'll go. It'll take about a month or two to get to where it needs to be in orbit to start collecting data. But I'll definitely be watching it, and I hope you will too. I think, yep, that is actually it. I didn't want to go into too much of the terrible scientific detail because, quite frankly, I probably couldn't explain it very well. But the thing is, I just wanted to give you a taste of what's happening and how simple observations of detecting how the light dims, you can get the orbital period, the size, and then the density, and then you go in with the other instruments and you find out the atmospheres, and who knows what's yet to follow. So watch the news for this. It's TESS, T-E-S-S, and also the JWST that was named for the first administrator of NASA, James Webb. And we'll see where this takes us. Any questions at all? Even if it's off this topic. Okay. All right. Well, thanks again for coming. Again, please remember the donation box. Anything at all will help. We also have a staff of QOs that are here, qualified observers. They'll have yellow name tags hanging around their necks. They'll be outside with telescopes or upstairs. Upstairs ready? Okay. Vlad will take some of you up. Don't everybody run upstairs, okay? The telescopes outside are very well at this too. And enjoy your evening.
Thank you.
Thank you.